Hi, I'm Tony Fowle. This is just one video in a series of tutorial videos showing how to use my motorcycle setup software, which you can see more details of on my website at www.tonyfowle.com.
The rear suspension part of this software is probably the most involved and probably the most used and most important. Initially, when we select the rear suspension, we're presented with a screen with 9 possible starting values for any design that we wish to analyze. If the particular design you've got isn't here, it's still likely that we can analyze it by just changing the input data. The important thing is that the type of rear suspension that we're analyzing is divided into 3 classes defined by the 3 vertical columns here. This is what's labeled as the simple type, where the shock at one end is directly connected to the swing arm and at the other end is directly connected to the frame. This case is the same, one end to the swing arm, one end to the frame, and this one, even though it looks different from the original one, is still the same category. Okay, we've got one end of the suspension fixed to the swing arm, the other end fixed to the main part of the chassis. This can be either monoshock or twin shocks, which would be useful in this case. If it's twin shocks, then we just need to put in the values for spring rate and so forth of the 2 shocks combined. This second class of suspension system is a rocker and link system, the link in green, the rocker in red. And this is defined by the fact that one end of the rocker is fixed to the swing arm and the pivot for the rocker is fixed to the chassis. Okay, so even though all 3 of these cases look rather different, they all fit into the same category. The link is fixed to the swing arm and the rocker pivot is fixed on the chassis. In some cases the link might be a push rod, as in this case, or in other cases it will be a pull rod, as shown here. The third class of suspension is still a rocker and link, but in this case, instead of having one end of the link fixed to the swing arm, one end is fixed to the frame. Okay, we can see that in all 3 of these cases. And the pivot for the rocker is fixed to the swing arm. Now, in any of these 2 main classes here, the shock, instead of having one end connected to the chassis, may be connected to the swing arm, as in this example of the Unit ProLink. Okay, for instance, we could see here it'd be very easy to connect that end to the swing arm. So we select one of these. Let's pick this one for example, and we start off with that case here. Now that will probably not fit the data of the case that you're actually trying to analyze, but all of the relevant data can be entered in here. Now, it's quite possible when you're entering in new data that some of it may not be compatible, and so when you first enter some data, the graphic won't automatically redraw to reflect the data that you've entered. For instance, if we go into a box, we get this button come up which asks us to click to redraw when the data entry is complete. So the best thing is to enter all of your data in first, and then when it's all in which case the graphic should be a proper representation of the valid design, then you can click on this button and it will redraw the graphic according to the data you've entered. The data that goes in, I think most of these things are fairly obvious. We've got the pivot height, which is the height of the swing arm above ground level. The X coordinates of various things are measured with the swing arm pivot being 0. We can see that from the coordinate box at the top here. Okay, so when I'm aligned on here, that's showing me that I've got, well, before I moved it, that I had coordinates of 0 and 370. Okay, there are 2 methods of entering data in for the measurements of the swing arm. We can just simply enter the length, which is OA, or XB and YB. Now, in anywhere where there isn't sufficient explanation of what the date is, where there's likely to be any doubt, there are little flyout help screens which will let you know what those symbols mean. In this case, we can see that XB is the distance from the swing arm pivot along the line towards the wheel axle to where the link or shock mounting is, and YB is the distance from that line to the position B itself. In some cases it's easier to measure that data in a different way, and we can select that by clicking on this alternative data button, which gives us a little pop-up screen where instead of entering the data more or less in an XY form, we enter it in as 3 different lengths. OA, which is as before, which is simply the length of the swing arm, and the distance from O to B, which is the distance from the swing arm pivot to where the spring or link mounts, and then AB, which is the distance from the wheel axle to that spring or link mounting. If the mounting for the shock is below the swing arm, then we just simply click on this tick box B below. Okay, and when we select that data, the software will automatically convert it into this form. Okay, it'll calculate these values for us. The suspension unit, we've got to enter in the X and Y coordinates, which is where it's fixed on the chassis. If we elect to have the shock on the swing arm, which we can do, then those measurements are no longer relevant and the data entry boxes disappear. The static length, that's just the length of the shock and the maximum stroke of the shock. The spring rate, the spring preload, they're all fairly obvious. If we have any top-out springs in the shock, then we can enter the data here. First of all, we enter in the spring rate of the top-out spring, and the top-out contact is the distance from the fully extended position when the top-out spring comes into use. Here we can click on this button to get a separate screen where we can enter in the details of any custom springs or bump stop rubbers that we might be using. We won't go into that now, that will be the subject of a separate tutorial video. Here we have the weight as measured on the rear wheel, rear tire, the same as if we put the bike on scale at the rear wheel. This is the weight of the rear wheel and brake disc and calipers, etc., the tire rolling radius. Here we have where we can enter in the details of the rocker and link. We enter in the pivot point in terms of X and Y coordinates, and then the measurements of the rocker, we have these symbols DE, DF, EF. Again, if we use the flyout help screen, we can see that DE is the distance from the rocker pivot to where the shock mounts. Now it doesn't matter whether the shock is on the left or right or above or below in the actual design. DE is always the distance from the pivot to where the shock mounts. Okay. DF is likewise, but it's the distance towards where the link mounts, and EF is the distance between the shock and link mountings. Link length, that's fairly obvious. The rocker orientation is less obvious. This is because when we specify the rocker details, there are 4 possible ways in which it could be mounted. For example, it could be, this is the correct way, but it could be mounted flipped vertically, or flipped horizontally, and or flipped vertically and horizontally. There's no easy way of entering in that information into the software other than through being able to view these 4 different orientations. So if we select a different orientation here, it will show us where the layout of the link will be. It's just drawn a partial graphic because in many cases it would be impossible, geometrically incompatible, some of these other orientations, in which case we wouldn't be able to draw a realistic graphic. Graph 3 will be the other way. We can see it's been flipped horizontally and the link actually goes forward rather than to the rear mounting. This actually could form the basis of a viable suspension, but we won't go into that here. Or position 4. So from looking at these 3 or 4 different orientations, we can see that in this case this is the one that represents what we're looking for, so we have one. So when we've selected the right orientation, we just click on this and then we get the full graphic again. In some cases we mount the shock on the swing arm, and in this case we can see that it would be structurally quite easy to do. We'd only have to add a small amount onto it, so it might be a useful candidate from the point of view of packaging, or not building another structure coming off the frame to do that. And we can specify that option by clicking on the shock on swing arm here, in which case we need to enter in some coordinates to represent the position of this on the swing arm. Well, if we go here, we can just see that that's roughly, it's got an X value of about 84, and the Y value is about 336, which down from here would be about 35 or so. So if we put in, say, 84 here and minus 36 here, we should get a layout that's pretty close to what we had before. Okay, we can see we were a little bit out with those coordinates, but if I make this, what do I need to do, a little bit less, say 33, then a bit closer, let's come down to say 27 maybe. Okay, 25. Oops. And well, we're fairly close to it. Okay, so we can see how we can add in the data if the shock is actually fixed to the swing arm. I'll untick that for now, and we'll go back to our standard setting. Here we can enter in data for the chain and sprockets, which is used for the calculation of anti-squat. We can put in the pitch of the chain in inches, because that's how chains are normally specified. X and Y coordinates of the sprocket center here, and the number of teeth on the front and rear sprocket, and that in combination with the pitch of the chain, the software will calculate the diameters of the sprocket, which is what's really needed. Here we've got the opportunity to exercise the suspension over the full range of movement, from full extension to full bump, as we can see here, which gives us a good guide to how the geometry of the suspension system will change. Or we can look at it in more detail by raising it up slowly here. Okay, so sometimes this is very useful to see if that we're not going to get into a situation which is impossible geometrically. When we've entered all our data in, to check the characteristics that we want, we just simply have to press the calculate and plot button. And we've got a number of predefined curves which we can access through the tabs along the top. The default one that comes up first of all is showing us the spring and wheel forces plotted against the vertical wheel movement. The red one is the wheel force plotted against the movement, which is the one that we're mainly interested in out of all of the parameters available to us. This is the one that defines the performance of the rear suspension. This is more or less by way of auxiliary information, which gives us the force in the spring for different vertical wheel positions. We can toggle, this dark line represents the static sag position as defined by the spring rates, characteristics of the suspension, and the load on the rear wheel that we've specified. Okay, we can toggle that origin so that this is 0. We just simply click on this button. The curves are exactly the same, the data's the same. It's just that now we regard our static sag position as being the 0 for the x-axis. Okay, we just toggle that back again. We can actually toggle the x-axis between the vertical wheel movement and the movement of the shock. Okay, so this is the shock compression, and we can see the same values plotted against that. In most cases we're interested in it plotted against the wheel movement, but there are occasions where against the shock would be useful. We've got various copy and print options here. We can copy the graph to the clipboard to paste into another program if we were writing a report, for example. Again, we can save that graphic to a file for further processing, or we can just simply send it the whole form straight to the printer. Okay. Other predefined graphs that we have here, we can see the wheel rate against the wheel movement. Again, we can toggle the x-axis base for that if we wish. We can also toggle the wheel rate values between the actual values, which are plotted on here in newtons per millimeter, or we can look at it as a percentage with the initial rate being defined as 100%. This is very useful because it gives us a very quick idea for the amount of progression in the rate that we have over the range. Okay, we start with 100% here, and we can see in this particular case it's quite highly progressive. At maximum we've got about 510%, so we've got over a 5 to 1 increase in progression in rate at the wheel throughout the range of motion. Here we can see the motion ratio as defined as the movement or velocity of the of compression of the shock compared to that of movement of the wheel. Now, quite often motion ratio is expressed as the inverse of that, the motion of the wheel compared to the motion of the shock. The reason it's plotted here is because if it's plotted the other way round, we may well get values approaching infinity, which doesn't give us a very useful graph. In this case, if we're getting into the situation where otherwise we'd be plotting a graph towards infinity and losing all the detail in the other parts, it would just simply plot down towards a minimum value of 0. There are two values plotted on this graph. The blue one is the actual value of the motion ratio, as I've just defined it. In this case, it starts off about 0.46 and ends up at around about 0.84. The red curve is a normalized value which takes this value as 1. Now again, like looking at the percentage for the value of the rate, this is quite useful because it just simply gives us a proportional increase in motion ratio over the range. Okay, here we started off with a value of 1 and we ended up with a value of 1.82. So we've got an 82% increase in motion ratio over the range. Here we can see the shock displacement against the vertical wheel displacement. That's simple enough. The swing arm angles throughout the range of movement. Here we can see the forces on the swing and arm pivot, horizontal and vertical forces, and also the resultant of the two. Now remember, this is purely a static analysis and we're just looking at the forces due to the spring on the shock. It would take a full dynamic analysis, which is outside the range of this software, to get the true forces because we would have to add in those from the damping. In the same way that here we see the swing arm pivot forces, we can look at the pivot forces on the rocker and in addition the force in the link. Okay, the tension or compression force in the link, depending whether it's a pull rod or a push rod. Here we can see the energy absorbed in the spring throughout the range of movement, but in fact it's usually only ever the final value that's ever of interest to us. Okay, now we can see all of the calculated data, some of which is plotted here in tabular form if we click on this tab. Okay, and so here we can scroll across for all of the parameters that we've calculated. And anti-squat is included amongst them, even though it's not included in the predefined graphs, because normally we would get a preview of this by going into the anti-squat screen and arranging parameters to get the values that we wanted. From this screen we can save the data in a variety of formats. Clicking on this button, we can give it a project name and some case notes if we want to. Let me just call that test, and we'll call this project. I will call this tutorial. Okay. Now we can save this data in 4 different formats. We've got ERD, which is the default value. Now this is the format that the internal plotting system uses, which will be the subject of another tutorial, where we can plot 10 cases or 10 different analysis on the one curve. SLK format is a general spreadsheet format which should be capable of being read by just about any computer based spreadsheet. A text file in tab delimited form, again most spreadsheets can import this as well as a lot of other programs, and probably the most popular for additional processing and graphing might be the standard Excel spreadsheet format, XLS. Okay, so we've got a wide range of options of saving the data. We can print the data, okay, just to the default printer, and we can add the data to a plot list, and that's part of the internal plotting thing. It would then be one of the 10 cases that we would plot, but as I mentioned, that will be part of the next tutorial, and that's what we access from this tab here. Now let's close this window and return to the main rear suspension screen. We've got a lot of options on here that we've not talked about before. One, we can save the project. Now where we save the project to a file, it's not only the rear suspension part that we have on this screen that we save. These buttons are scattered in different places throughout the software, and they all save the whole project, which includes the rear suspension, the front forks, as we've last entered data for them, and a few bits of data that aren't relevant to either the rear suspension or front suspension, but that we need for the whole bike analysis. And when we load the data, load a project, again we load the whole thing back in. I won't go into the loading and saving now, because we'll do that in the tutorial video on the master data file. There are cases when we normally first enter the data in, due to measurement tolerances and errors, it's likely that the wheel will not be shown here sitting on the ground. For instance, say we made an error of a couple of millimeters in measuring the shock length. Say in fact we thought it was 227 instead of 225. We can see here that it shows the wheel is not sitting on the ground, because so far we've kept the chassis of the motorbike constant, and we've just changed this length here. We didn't measure it accurately enough or whatever it was, and we can see that shows the wheel not on the ground. Obviously that's not what happens in reality. What will happen in reality, if our link was too long, is that the rest of the bike would lift up and obviously the wheel would sit on the ground. If we click on the Adjust Attitude button here, what it will do is it will rotate the whole bike about the front wheel spindle and recalculate the coordinates of the swing arm pivot, the sprocket center, and the rocker pivot and the shock pivot if relevant. So we click on that, and well, it gives us the option of whether it gives us new values for the rake and trail. It gives us the option whether we want to update the global project data, and I'll just, normally you'd want to click on yes for that, and we can see here that it's recalculated the coordinates. Okay, the pivot height was 370 before. We can see it's about 2 3/4 increase that we needed to put the wheel, align the wheel with the ground. So normally you would do this when you put in the data as accurately as you can measure it, and you still see some error between the wheel height and the ground. Here you can see the appropriate values. In this case it's now 0, the error. One useful feature is this goal seeking feature. What this enables us to do is to, if we've got a particular design like this and we want to change the springing characteristics over generally a relatively small range. We don't we'd normally completely redesign it if we wanted totally different characteristics, and we can do that through this goal seeking feature, and we can select different parts, different parameters of the suspension that we will change over a specified range in order to achieve our change characteristics. So in this case, the shock mounting means that we're going to allow this mounting to move within the specified range to see if we can change the characteristics of the system closer to those that we want, or we could change the link mounting position. Okay, that will be where the link mounts on the swing arm here, or we could change the rocker pivot, or the rocker to shock length, or the rocker pivot to link length. So we can specify any of those. In this case, just to keep it simple, let's say we're going to see if we can change the characteristics closer to what we think might be desirable in practice by changing the shock mounting position. So we can draw a box which specifies or which limits the range of movement around here. Now don't be tempted to draw this box too big. In reality, you've probably only got a limited range over which you may be able to reposition the shock mounting on the frame. The same goes with any of these other changes. And also in some cases, if you specify too wide a range, you may put the suspension into a situation where there'll be locks, or you'll get impossible geometry. Okay, and then you'll just get errors when you try and do the calculation. So limit the range of movement within sensible limits. So when we've done that, we click on it, OK, and we get this screen. This graph shows us the value of the normalized wheel rate versus the displacement, and remember that went from about 100% to over 500%, and we see the thing here, but it's expressed against 1. Here we have the displacement intervals equally spaced according to the computer dividing up the total movement into 10 different sections, and we've got the base rate, which is what we had with our existing system. Here we have the goal that we want for the type of characteristics. Okay, by default it's the same as the base rate, so we can change any of these values. Now in order to save work, we don't have to specify exactly what our new curve will be. In general, we want to do something like increase or decrease the rate at the end of the suspension movement. In this case, just say we want to reduce that down. We think the progression is a little bit high, so let's say we want to knock that down to maybe 4.5. Okay, and so we've got a value here. We could now just do a goal search on that alone, but we wouldn't actually be expecting or wanting the curve to come up and follow this line. We'd be more interested in it coming from here and smoothly matching into the rest of it. And we could enter all these other values in closer to that. But being a little bit lazy, we just specify the last value and search and see how close we can come. Okay, so we can see this is the value that the software is determined. This is a characteristic that the software is determined we can get by moving the bottom of the swing arm around a certain amount. Now maybe we get closer to our final value that we wanted if we did actually bring this down a little bit. In this case, let's say at 110, that'd be down to 3 point. Let's go a little bit below to try and force it. Say 3.66. Okay, let's put this in at 3.66, and now we'll search again, and we'll find we're pretty close to actually getting what it was that we wanted in the first place. So if we're happy with that, we can go ahead and press this button to use that data. But before leaving this screen, let's just quickly look here. What we can do, we can clone our desired characteristic from a previous analysis. Say for example we had a Honda, and we wanted, and we but we didn't like the characteristics of the suspension, and we had tried a Ducati, for example, and we were quite happy with the amount of progression on the back of the Ducati. What we could do is analyze the Ducati first and save the details of the Ducati, and then in this case we'd come in to optimize the Honda, and we could import the Ducati data from here, and that would form our goal, and then we could see if we could achieve that with the Honda system. Okay, or whatever make. It doesn't even have to be a different make. Say for instance we had on a race bike we had a particular setup which we liked, and we had a new model of the same race bike, but the suspension characteristics were a little bit different. This would enable us to see what we'd have to change to get back to what we really wanted. Okay, so in this case, let's use that data, and now we'll see that we've got a progression from say 1 to 4.5, which will be 450% roughly. So let's use this data and come back to this screen. We can see here that the bottom of the shock has moved forward a little bit. We didn't actually make a note of what the X position was originally, but that's moved. But if we now calculate and plot with the new, we come back here to the wheel rate, we can see, if we look at it as a percentage, that instead of going up over 500, we're now on the 450. So by using the goal-seeking method, we could see what modifications we needed to make to the suspension to achieve a particular goal.
Well, that's it for now. To make sure that you don't miss any more of these tutorial videos on the motorcycle setup software, I suggest that you tick the like button on this one and subscribe to my YouTube channel, Motor Chassis. For more information about the suspension setup software and my book on chassis design, I suggest you visit my website at www.tonyfole.com. Thanks for watching.